Your experiment fails and you start doubting yourself. But the real culprit might be the plasmid backbone you chose, which was incompatible with your biological system. Today I'm going to walk you through why backbone architecture matters and how copy number, selection markers, or co-expression elements can make or break your experiment. The plasmid backbone is the structural scaffold that supports the expression cassette. It determines how the plasmid behaves as a physical and replicating entity. If the backbone is wrong, the experiment fails, even if your gene and cassette are perfect. Origin of replication. The copy number is controlled by the origin of replication. It dictates how many copies of that DNA exist per cell. High copy plasmids give great yield but impose metabolic stress, while low copy plasmids are used to stabilize toxic inserts. But copy number is an average and it is not fixed. It varies with strain genotype, growth phase, nutrient availability, or insert toxicity. If your plasmid behaves unpredictably, origin of replication and copy number is often the culprit. Selection markers. The primary purpose of selection markers is to identify and isolate those bacteria that have successfully taken up your plasmid. They are the primary mechanism that determines whether your plasmid persists in a bacterial population, but they do not inherently make the plasmid biologically stable, as plasmids can still be lost or undergo mutations. Also, you have to consider the characteristic of the antibiotics. For example, ampicillin is highly unstable and degrades rapidly. Kanamycin remains stable for longer periods, therefore is widely used. Puromycin sensitivity varies tenfold across mammalian lines. The neomycin resistance gene is a weak selectable marker, so it requires a strong promoter. Copy number control elements. These elements sit close to the origin of replication because they directly regulate how frequently the plasmid initiates replication and fine-tune replication frequency. But these regions are sensitive. Mutations or inserting sequences too close to them can destabilize copy number regulation, leading to unpredictable plasmid yields, altered metabolic burden, or even growth defects. Multiple cloning site. The multiple cloning site is your entry point for cloning inserts, but not all multiple cloning site regions are equal. Poorly designed multiple cloning site regions can introduce cryptic promoters, terminators, or secondary structures that interfere with expression. Orientation, restriction compatibility, and recombination hotspots all matter. Insulators and scaffold sequences. Advanced plasmids include insulators or scaffold sequences to stabilize expression and prevent interference between backbone and cassette. They are positioned flanking the expression cassette to reduce enhancer interference, silencing, and transcriptional noise. But their performance is highly context-dependent and cell type and chromatin state matter. So now you may ask, which are the non-negotiable elements required to successfully keep and grow a plasmid in bacteria? If you said origin of replication and the selection marker, bravo, you are right. Without origin of replication, the plasmid cannot exist inside the bacteria and will disappear after cell division. If the resistance gene mutates so that it no longer functions, the bacteria can copy the plasmid perfectly, but the antibiotic kills the cell before it ever gets a chance to divide. Everything else on the plasmid, like your inserted gene of interest or the promoter, can technically be mutated, deleted, or rearranged, and the bacteria will still happily grow. Your plasmid backbone isn't just a container, it's an active molecular machine. Copy number, selection markers, control elements, MCS design, and insulators all shape your experimental outcome. Choose wisely, validate empirically, and your data will sing. Choose poorly, and your experiment will fail.